Okay, so we've got CE congruent to DB, and they also tell us that we've got angle AEC, which we've already got marks in it, and ADB, those angles are congruent. Now our goal is to eventually show that triangle CAD and triangle BAE are congruent. Okay, knowing this information. Okay, so this is a little bit, I think, maybe somewhat of a messy question, but look at this. We're trying to prove. Let me just highlight them so I can talk about them a little bit easier. Trying to prove that green triangle congruent to that green triangle, right? And so far, you have a side and an angle, correct? So let's think about our options that, if we've got side, 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 angle, angle, and angle, angle, side, obviously we're not going to use that one. Side, side, side's not an option, okay? But it opens the door to all the other ones, doesn't it? Okay. So we've got to figure out which angle or which additional side would maybe be easiest for us to show congruent. So if I want to, let's say, use angle, side, angle. Let's say I want to use angle, side, angle. Then would you guys agree that I'd have to be able to show this angle here, C, congruent to that angle there, B? Is there anything up there that either in vocabulary or given information that's going to allow you to conclude that angle C and angle B are congruent? Say it again. Okay, so that they correspond here in their name, but we can only say that the angles are congruent then if these triangles, if those were triangles that were congruent. So we can't say that yet. Okay, how do you know that? Uh-huh. Uh-huh. Okay. So, and talking about angle C and angle B, we can't show those congruent. So, angle, side angle is not going to be an option. Okay. Of a what? It's not isosceles. You don't know it to be isosceles, right? Now, and that's what they do on purpose. They make them look like they're isosceles, but you don't know that yet. So you can't say one way or the other, okay? But what Joel said is he knows that that angle right there is congruent to that angle right there. Now let's walk through the logic of that, okay? So if we look at angle CEA, and angle AED, we can say they are supplementary, correct? Okay, why are they supplementary? What do they form? They're a linear pair. So that was the linear pair postulate. Okay. Can you then say the exact same thing on the right-hand side over here? Yeah. Okay, so I'm going to say angle BDA and angle ADE are supplementary, and it's still because they're a linear pair. Set AEC to AED. Yeah, we did that right here. No, I didn't name it. I named it CEA, but AEC is fine. Okay, well, yes, but based off of what we have so far, we can't jump from this statement yet to showing the sides congruent. But that's where we're going with it. So we have to make sure when we write a proof for our audience, that our audience is able to see how did somebody go from two sets of angles being supplementary to now sides being congruent, how they make that leap. And there's a couple different ways we can do this. Think about this, and I think it's easiest and most obvious that when using vocabulary, if they're supplementary, what does that mean we can do with those two measurements? But what's supplementary mean, though? By definition, yeah, they add up to 180. So I want to say that. And I can do the same thing about angle BDA and ADE. That's definition of supplementary angles. All right, so we've got that. Remember in the past when we saw questions that in two lines, if they both had 180, and it doesn't have to be 180, it could be about 90, and other proofs could be some other value, but if we have these two things being identical, what does that tell you about that compared to that? They're the same. Okay, so step 4 will be that the measure of angle CEA plus the measure of angle AED is equal to the measure of angle BDA plus the measure of angle ADE. And that's substitution. All I did is I substitute. Basically, this red line is that line right there, but where I saw 180, I replaced it with what the next line said 180 was equal to. Okay. Now, that looks like we got two things on the left added together, two things on the right added together, and if I look at the individual parts, CEA on the left, I never see CEA again on the right. AED on the left, I never again say AED again on the right. However, there are, whenever you get a statement like this, chances are you're going to want to be able to remove something from both sides. And the only way they can remove something from both sides, if there is something that is, in regards to its amount, the same. It might not look identical name-wise, okay, or notation-wise, but there is an amount on the left-hand side that is exactly the same as an amount on the right-hand side. And that amount comes from this phrase right here. Is AEC, which would be that angle right there, and ADB, which is, and I wrote them backwards, but it's that one right there, right? Okay. They are measuring, if the angles are congruent, are those amounts, those measurements the same? So what can I do with those if they're the same? Take them out. So that's going to leave me with the measure of angle AED equal to the measure of angle ADE. So I took that one out. I took that one out because up here it says they're the same. And that leaves then that one equal to that one. And if I take something out because it's on both sides, it's the same amount, what operation is just removing something? Is it great subtraction? Subtracted whatever this, maybe this was 40 degrees. So if it was 40 degrees there, it was 40 degrees over here. So I can subtract 40 from the left as long as I do it from the right. So that's a subtraction property of equality that we use inside equations. So now, and I'm just going to, this is usually what we do when we have equal measurements for angles. we just jump to say that the angles are congruent then. And the reason will be definition of congruency. Okay, so when we were up here in statement 2, Joel was able to make us realize that we had some segments congruent. But before we're going to make those segments congruent, or argue that they're congruent, we had to come up with this first. Because now, look at statement 6, it says AED and ADE are congruent angles. Well, AED is that angle there, ADE is that angle there, right? So if I'm looking at just that blue triangle then, if these angles are congruent, but doesn't that side have to be congruent to that side? That make sense, everybody? So I'm going to say segment AE is congruent to segment AD. Segment AE is congruent to segment AD. Does anybody remember why that's the reason? Not because an isosceles triangle says that basically you can name something isosceles by knowing that it already has two sides congruent, or if you have a triangle that has two sides congruent, you can name it isosceles. But what we knew is just that these angles were congruent. Okay, but you guys are saying that the logic that you're using right now is that these base angles are congruent because the triangle is isosceles. Okay? We don't know what isosceles. It's the reverse of it, the converse of that. If we have base angles if we have two angles of a triangle that are congruent, then the sides opposite are congruent. Does that make sense? And then that's what allows you to make sure or identify that triangle as isosceles if you need to. Okay? So the reason here, you can write it out two different ways. I'm going to say converse of isosceles triangle theorem, which remember what that says. The converse of isosceles triangle theorem says if two angles of a triangle are congruent, then the sides opposite those angles are also congruent, which is what we went through. Okay? And then if sides opposite are congruent, that means two sides are congruent, then you could call it an isosceles triangle, right? Okay? But now let's think about this. Are those red sides that we marked, are those sides that are in the green triangles? Yeah, so now what parts and in what order do you have congruency over here in these green triangles? Okay, so now you got side angle side. So let's say at that green triangle, let's go, I'll just call it CAD. Actually, change this real quick. I didn't pay attention to what we were trying to prove. Call this CAE in triangle C or BAD. That's what I wanted to prove. So we want to prove those two green triangles congruent. So now, do we have that? Yeah. Okay. So I'm going to say now that triangle CAE is congruent to triangle BAD. Okay. And that would be because of side, angle, side, correct? Side, angle, side. Now, that was probably maybe one of the lengthier proofs we've done. Okay, and we could even go further. There's more information that we can come up with now. Think about this. If those two triangles are congruent, is that congruent to that? So then that would be that overall triangle would be isosceles, wouldn't it? Okay. Would angle C, if that overall triangle is isosceles, would angle C now be congruent to angle B? Okay, and there's a couple different reasons why. One, base angle is isosceles triangle, but they would be congruent because the CP, CTC of those two green triangles at the beginning as well. There's a lot of stuff here that we can now conclude by being able to show that these two triangles attached to the side are congruent. And I should have paid attention to this when when we started, I thought I wanted these green triangles to be congruent. I thought that's what I had written here. But what this is saying actually, and the approach would be very similar, but they're trying to show that that triangle there is congruent to that yellow triangle. So you got overlapping triangles. So but that approach to showing those congruent would be very similar to what we just did. Maybe we'll do that in the next couple of days. Okay, so that's great. That's awesome. Now, you guys know that writing proofs kind of stinks, right? Okay, this 8 steps was not all that enjoyable, but we could have maybe circumvented a little bit of the work. Okay, do you guys remember when we had a theorem at one point that said, I'll see if I can type it out here. It said if 2 angles are supplements to the same angle or congruent angles, then those 2 angles are congruent to one another. Okay, let's think about that phrase right now. If 2 angles are supplements to the same angle or congruent angles, would you guys agree? So AEC and ADB, based off the given, they are that one right there and that one right there. Does that make sense? Would these be 2 angles that are supplementary to congruent angles? Does that make sense, everybody? Okay, so if 2 angles are supplements, so these 2 angles are supplements to congruent angles, then these 2 angles are congruent to one another. Does that make sense, everybody? So we could have circumvented step 3, step 4, and step 5, and wrote step 6 right after step 2, and used that theorem that says if 2 angles are supplementary to congruent angles, then they're congruent to one another. And that would have shortened this proof by 3 steps. Does that kind of make sense? And that's the benefit. That's why we have theorems. That's why we try to learn these theorems and postulates, so that when we come across something that is needed to be proven, we need to see the reason why it's existing. There's alternatives to writing, 8 steps, 10 steps, 15, 20 steps. And maybe you can do something in maybe 4 or 5 steps. Okay. Now, when you guys came in, and Connor asked, what class was that stuff that I had on the board? So my college algebra stuff. Okay. Today I introduced them to a theorem. Okay. Which algebraically can be proven. It's a theorem, and there's logic on why it works. Okay. And this is the proof. Now, it's not 2-column proof, but this is what we go through in like an algebra class. Now, you don't do this, and I'm not even making my kids right now know how to do this. But when you go to college, and I wish I would have known this, somebody would have opened my eyes to it when I was in geometry class, and I could understand proofs better at that point, because then it would have made my college experience a little bit better. When I got to college classes, some of my college classes for 16, 18 weeks in a row, this is all we did. Okay? And we didn't spend any time on specific problems like, last year you would factor stuff, right? So this is a proof for factoring. You guys remember seeing things like x squared plus 5x plus 6? Okay? Well, this is a theorem that allows us to factor something like this. Okay, something a lot longer. Okay, but it uses a similar approach to what you guys learned in Algebra 1 for factoring something like that. Okay, but if I would have known when I was in geometry in high school, and then Algebra 2 and college algebra, when they introduced and talked about this stuff, and they might have said, you don't need to know this for this class, but it's going to be, you might encounter it at the next level. Okay, I would have taken that stuff a little bit more serious. I would have learned these things a little bit better, because it would have made my college experience with those college classes in the algebra, and I would have understood the algebra a lot easier. Does that make sense? So if you're a person that has interest in like engineering, the medical sciences, those types of things. When you're going to use mathematics, you're going to encounter courses where you're doing a lot of proof work, and if you understand proof work and the necessity of theorems and definitions and learning them and retaining them, it makes your life a lot easier. Okay, I'm going to stop there with today's information. I do have a worksheet for you over isosceles triangles, and it's going to be due on Monday. And there is, I don't have it posted yet, but I will post it here within the next few minutes. There's going to be a place that you need to type your answers into on Math Excel.